So the remainder, when we're talking about estimating or approximating with Taylor polynomials, is the difference between the function and the polynomial. So Rn remainder of x is f of x minus Pn of x. The absolute value of this remainder is the error that we looked at in our last example. And we want to talk about this remainder because the absolute value of that is the error, and it's important to be able to look and talk about how accurate our approximations are. So we have Taylor's theorem, which is sometimes called the remainder theorem. Let me back up for a second. The important thing about the remainder is the remainder increases in magnitude. In other words, it gets larger as you move away from the center of the polynomial. So if you've got a polynomial centered at A, the farther you get away from that value A, the larger the remainder is going to be, and the larger the amount of error would be. The other thing to keep in mind is the remainder decreases in magnitude, gets smaller, gets closer to 0 with larger values of n. In other words, the more terms you use in your polynomial that you're using to approximate, the more accurate your approximation would be. So kind of what's implied here is that if you had an infinite number of terms, then you would have something that was exactly equal to your function f of x. So again, talking about remainder, there is Taylor's theorem, which is sometimes referred to as the remainder theorem, which is different from the remainder theorem that you may remember from your algebra courses. For function f, we have to have continuous derivatives up to the n plus 1 derivative. So in our nth degree Taylor polynomial, we'll use derivatives up through the nth derivative. Well, working with the remainder, we're talking about what comes after that polynomial. So we're looking at the n plus 1 term, kind of. So our function has to have continuous derivatives on some open interval that contains the center point A. Our function, the exact value for f of x, is the sum of the polynomial approximation Pn of x plus the remainder. And the remainder is going to be equal to the n plus 1 derivative evaluated at c. And we'll talk about what that is in just a second. Divided by n plus 1 factorial. So that's the coefficient of the term. And then you're going to have x minus a to the n plus 1 power. That is the remainder. Absolute value of that would be the error. Okay, and this is going to be true for some point c between the value of x that you're approximating and the value of a that's the center of your polynomial. Now the key is, we usually don't know what that number c is. We don't have a value for c. So what we kind of have to think about is, what is an upper bound for the absolute value of that derivative evaluated at c? So if we can come up with some upper bound that we know all of our derivative values are going to stay less than or equal to, then we can make this work. And there's another theorem that helps us kind of think through that. So assuming there is some fixed positive number m that is basically an upper bound for the value of that derivative for all values to c between x and a, then the error, absolute value of the remainder, will be less than or equal to that maximum number m times absolute value of x minus a to the n plus 1 power divided by n plus 1 factorial. Now let me kind of explain that. I'm bothered by the way that's written. Okay, there's our remainder theorem. We've got the derivative evaluated at c divided by n plus 1 factorial. So we're saying there is some m that is an upper bound for that derivative. So I would want to write that as m over n plus 1 factorial, and that's going to be positive because we're saying m is a positive number. And then that's multiplied by the absolute value of x minus a to the n plus 1 power. And to kind of put it in the format that you see in your textbook and that I had written here originally, all they've done is, instead of having the n plus 1 in the denominator under that maximum value m, we're going to put it under the x minus a to the n plus 1 power. So m times absolute value x minus a to the n plus 1 power all over the quantity n plus 1 factorial. The key is to find that value m. And the interesting thing is that, when all of us do a particular problem, we may come up with some different value m. And you kind of want to think about the smallest value that you could come up with that your derivative has to be less than. All right, here's an example. We want to estimate the amount of error OR in the cosine of 0.45 using a third degree Taylor polynomial centered at the origin. So centered at 0. At, come on computer, 0. Alright, so we're talking about R3 of 0.45. Okay, well, according to our formula, R3 of 0.45 will be less than or equal to some number m times the absolute value of x, which is 0.45, minus a, which is 0, raised to the 4th power divided by 4 factorial. Okay, so what we're dealing with here is our function f of x is cosine of x. Okay, and think about it, the derivatives of this function all of them are going to be in the format that they're either plus or minus the sine of x, or they're plus or minus the cosine of x. So if you think about taking the derivative of the function f of x, over and over and over again, you're either going to have sine or cosine, or the negative of sine or cosine. And I know that the maximum value for a sine or a cosine function is 1. So we're going to let m be 1 because the derivative at any point c has to be less than or equal to 1. So, okay, it's the error, so it should be the absolute value of the remainder. Absolute value of the remainder, R3 of 0.45. Okay, I'm making a mess here. 0.45 parenthesis absolute value has to be less than or equal to 1 times 0.45 to the 4th. Absolute value doesn't change it because it's positive, because I'm subtracting 0 over 4 factorial. So grabbing your calculator and evaluating this expression, we'll find that the amount of error using a third-degree Taylor polynomial to approximate cosine of 0.45 is 0.00170859, and so on. The trick, the hard part of this, is to come up with this value for m. With a sine or a cosine, it's pretty straightforward. With another type of function, you're just going to have to pick some number that you know is greater than all your derivatives.